previously in Chapter 11, we had an introduction to the three-dimensional rectangular coordinate system, vectors, and the two types of products that can occur between vectors, namely the dot product and the cross product. We're going to still remain working with vectors, but we're going to switch gears a little bit and focus on parametric equations of lines in section 11.5. You might recall back in Calc 2, before we talked about polar coordinates and polar equations, we began with parametric equations. So this should look somewhat familiar from Calc 2. However, we're going to generalize things into 3 dimensions rather than 2. Let's get started first with theorem 11.5.1. Part A states that if you have a line in R2 that passes through the point with coordinates x0, y0, and is parallel to the non-zero vector AB, then it has the following parametric equations. X equals x0 plus AT, y equals y0 plus BT. So if you recall back from algebra, we had the common equation of the line y equals mx plus b, where we understand m to be the slope and b to be the y-intercept, which is a point on that equation of that line. In this case, it's very similar here. T is our independent variable, which is taking the place of x. A is the vector that governs the direction of our line, in other words, our slope. So our A and B components here take the place of M, and then our point, x0 and y0, occurs out here. So if you kind of just recall the y equals mx plus b formula, that might help you remember these equations. Similarly, if we're working in 3 dimensions, the only difference is we're going to add this z equation here. Now, if we want to restrict our entire line to a single line segment, all we need to do is restrict the parameter appropriately. Typically speaking, if you're moving from point 1 to point 2, your restriction is going to be to restrict t between 0 and 1. However, it does depend on which vector you use, and we'll see some examples of that. So let's jump into our first example here. Find the parametric equations of the line through P1 and P2, and also for the line segment joining those points. All right, so all we're given here is 2 points, P1 and P2. In order to find an equation of a line, we need 2 things. We need a point and we need a vector. Now we have 2 points, so we're okay on the point front. But for the vector, let's go ahead and let's find the vector from P1 to P2. But you could just as well find the vector from P2 to P1. So remember, you always take your terminal point minus your initial point. So 5 minus 3 and 1 minus a negative 2. So that gives me the vector 2, 3. All right. Then pick one of these points to use to find your equation of your line. I'm going to use P1. And now what I'm going to do is I'm going to look back up here at part A of the theorem and write out my parametric equations. X equals, take the x component of the point, which is 3, and tack on the x component of the vector, 2, times t. And then do the same thing for the y components. Y equals negative 2 plus 3t. These 2 equations are your parametric equations for the line. If we just want the line segment, all we need to do is restrict our parameter t. So notice if you plug in 0 for t, here and here, if you plug in 0, you're going to get P1 back out because that was your starting point. So the t terms will 0 out and you'll get 3, negative 2. So we want to begin at 0. And then we want to go up to 1 and just plug in 1 for t and test it out. If you plug in 1 for t at x, you get out 5, y, you get out 1, and sure enough, that gets you to P2. So this is a set of parametric equations that will result in the desired line and also the line segment between P1 and P2. Now, notice that we made a choice here, 2 choices in fact. We made a choice for our vector to travel from P1 to P2 as opposed to from P2 to P1. Had we switched that, our vector would have been negative. And furthermore, we made a choice to work with point P1 to find our equation for the line. So let's just suppose that instead we use the point P2. So let me pick a different color here. So suppose we used point P2. All right, how is that going to differ when we find our parametric equations of lines? So now using P2, which is given right here, we have x equals the x coordinate of our point, which is 5. We're still going to use the same vector. So the x coordinate of the vector is 2t. And similarly for y, we have 1 plus 3t. Now, when I look at these parametric equations, as opposed to the ones in black, these are visibly different. As it turns out, these are both equally correct. And so first of all, let's figure out what our restriction would be on t. So if I plug in 0 for t, now notice that that is getting me to P2. So that's actually going to be my upper bound. And if I want to go backwards to P1, since I started at P2, I need to go essentially negative in time. I'm going to go -1, and let's just double check that. If I plug in -1, x becomes 5 minus 2, which is 3. Y becomes 1 minus 3, which is -2. And sure enough, that gets me to P1. So this is equivalently an equation, a set of parametric equations for the desired line and also the restriction on the segments. Now, how can we analyze this and rationalize that these are in fact the same? So this may be a little bit silly, but let's talk about our understanding of time. We have certain increments of time that we use to measure units of time. We have seconds, we have minutes, we have hours. But suppose for a moment that we had some sort of an alien visiting us, and they also had a concept of time, but their units of measurement were not the same as ours. So maybe their second was equal to 2 of our seconds. So what they were measuring would seem half as much as what we're measuring. But it doesn't mean that their measurement is wrong. It just means that they parameterize it differently. The same thing is happening here. And so to see this equivalence between the two, if we substitute T1 equals T minus 1, so we're just doing a shift, then what happens? So I'm going to substitute this into the green equations above. X becomes 5 plus 2 times T minus 1. And so if you distribute this, we're going to get a 5 minus 2, which is 3 plus 2t. And y would be 1 plus 3 times t minus 1. That would be a 1 minus 3 is a -2 plus 3t. And sure enough, that exactly matches what we had over here in black. So just by shifting that parameter value 1, we were able to identify that these are correct. This is an important thing to note, that when you're working out these problems, your choice in both the vector and the point you're using is going to dictate what your answer looks like. If you flip to the back of the book and your answer looks different, that doesn't necessarily mean that your answer is wrong. So the best way to test it is to plug in these parameter values that restrict your segment. If everything is linear and if you're traveling from one point to the other, then your answer is correct. It's just an equivalent format. Let's do another example here, and we'll just do it in one format. This is the same setup, but we just have 3 dimensions here, so we're going to be finding an x, y, and z parametric equation. So first, let's find the vector p1, p2. So that's going to be 2 minus 5 is -3. 4 minus a -2 is 6. 2 minus 1 is 1. So here's our vector. And again, I'm going to just arbitrarily choose to work with P1. But as we just showed, you could work with P2 just as well. So for my x component, I have the x coordinate of the point plus the x coordinate of the vector times t. Similar for y. Similar for z. And then go ahead and tack on your restriction for t. So if I plug in 0, I get 5, negative 2, 1. It's whatever point you started with is what your 0 value will be. And then to get up to P2, you can plug in 1. That would give me 5 minus 3 is 2. Negative 2 plus 6 is 4. And 1 plus 1 is 2. That gets me to P2. So these are the parametric equations of the desired line, as well as the restriction on the parameters for the line segment. All right, sometimes it's convenient to express parametric equations in a more condensed format. So suppose we have these x, y, and z parametric equations. We can express it in the vector equations in the following way. You'll notice that we have these vector brackets. So we have vector x, y, and z equals, and then I'm just plugging in here the x component, the y component, and the z component as is shown up in these parametric equations. And then you can further break it down and pull off the points and the vectors. One other thing to note is you can also write these out in IJK notation. So equivalently, you could say x I hat plus y j hat plus z k hat equals, and we can write x naught I hat plus y naught j hat plus z naught k hat plus AT I hat plus BT J hat plus CT K hat. All right, so you'll notice I don't use this notation as much because I find it a little bit clunkier. I tend to use the bracket notation, but the IJK notation holds just as well here. All right, so our next definition is for a vector equation of a line. We already talked about parametric equations of a line, but now if we want to write it in this condensed format, what's that going to look like? So in R3, let R denote this arbitrary vector x, y, z. R naught is a particular vector going to the particular point x naught, y naught, z naught, and v is some other vector a, b, c. Then the equation R equals R naught plus TV is a vector equation of a line in R3. And then I just made a little note here that if you want to reduce it down to 2 variables or 2 dimensions, you can do the same as well. So for problem 5, what we're given is vector equations of lines, and we want to break them down to the parametric equations and then also pull off a point and a vector that's parallel to this line just by inspection. There should be no work to show on these problems. It's making sure that you understand the vector equation notation and that you can switch back and forth swiftly between parametric equations and vector equations. So first, the parametric equations. All we're going to do is we're going to pick off all the x components. So x equals 2 plus t. And then the y components, y equals negative 3 minus 4t. So this is the parametric equations equivalent to this vector equation. And then we want to pull off a point and a vector. So for the point, our point is just R naught. So I'm going to pull off these coordinates and write them as a point, 2 comma negative 3. Notice I'm using round parentheses as opposed to square brackets because this is a point, not a vector. The vector is always attached to the independent variable, in this case the parameter t. So our vector is 1, negative 4. And that's it. That's all we're looking for on these problems. Part B is the same. The only difference is they're writing it out in IJK notation. Otherwise, everything else follows. If you would like, you could write it back into that angle bracket notation, which would be x, y, z equals 0, 0, 1 plus t, 1, negative 1, 1. Right? This is an optional step. It's not required. Now let's write out the parametric equations. X equals, I'll write 0 plus t, but of course you can leave off that 0 there if you want. Y equals 0 minus t. Z equals 1 plus t. So these are our parametric equations. Our point here, was somewhat degenerate. Remember, that's that beginning part, and we only had a k-hat component, so it was 0, 0, 1. And a vector parallel to this line is given by 1, negative 1, 1. Again, those coefficients are just being pulled off of the item that's attached to the t parameter. All right. So now we want to find the parametric equations of the line through the point 0, 3 that is parallel to the given line there. So one thing that we know for certain is we know a point, we know a point on this line, 0, 3. The only other thing that we need in order to find the parametric equations is a vector along it. Now what we know is we want to be parallel to the line given. So if we want to be parallel, that means that they're sloped in the same direction, so to speak. That is, whatever vector is governing the parametric equations given to us will also work for our equation. So I'm just going to highlight in on the t components because that's where our vector components come from. So pulling off those coefficients, I have 1 and negative 2. This is the vector parallel to the parametric equations of the line given to us. We can use it for our line as well. So now piecing it all together, I have x equals 0 plus t, y equals 3 minus 2t. And that's it. All right, one more example to finish off this page. Find the parametric equations of the line that is tangent to the parabola, y equals x squared, at the point negative 2, 4. Now, you most certainly do not need to sketch this, but let's just take a look at what we're working with. All right, here is the parabola y equals x squared. And we want the parametric equations of the line that is tangent to the parabola at negative 2, 4. So we're looking at this line. All right, so once again, we have the point for certain. We know what the point is. What we need to find is the slope of that tangent line. So when you think of slope of the tangent line, one thing should come to mind, the derivative, right? So I'm going to find the derivative of y, which is just 2x, but I specifically care about this when x is negative 2. All right, so that gives me a slope of negative 4. So that's all good and well, but how does this translate into a vector? What is negative 4 in terms of a vector? Well, if you think of negative 4 as negative 4 over 1, recall that slope is rise over run. So the run is always referring to x, and the rise is always referring to y. So what that means is our vector v can be written as the run x and the rise y. So for every 1 unit in the positive x direction, that means every 1 unit to the right, we're going down 4 units. All right, and so now we have what we need. X equals the x coordinate of the point plus t, where its coefficient is 1 due to the vector, and y equals 4 minus 4t. They didn't ask us for a line segment, so we don't need to give any kind of restriction on our parameter t here. All right, so we have several more examples to finish out this section. All right, so for 24, where does the line xy equals 4t, 3t intersect the circle x squared plus y squared equals 25? So in order to identify how to move forward with this problem, we need to really understand what it means for a line to intersect a circle. What is happening at those points of intersection? So let's call one of those points of intersection just x comma y. What that means is xy satisfies the equation of the line, and it also satisfies the equation of the circle, right? That's what it means to intersect. So if I take this vector equation of my line and I write it parametrically, I could say x equals 4t and y equals 3t. So if this line is going to intersect the circle, well then, this x and this y had better also satisfy the equation of the circle. So I'm going to plug those values in. 4t squared plus 3t squared equals 25. So I have 16 plus 9. So I have 25t squared equals 25. In other words, t equals plus minus 1. Don't forget that plus or minus, right? If you only take the positive square root, you're losing one of your 2 points of intersection. All right, so did they ask me for the parameter values at which the line intersects? No, they asked me for where. In other words, they want actual coordinate points. So what we're going to do is we're going to take these parametric equations and we're going to evaluate them at plus or minus 1. So that gives us plus or minus 4, plus or minus 3. Now this is in vector notation, so let me write them out as points. 4, 3, and negative 4, negative 3. All right, and so this is where the line intersects the circle at those 2 points on the circle. All right, we have a similar question here. We want to know where this line in 3 space intersects the plane. So when you're talking about lines intersecting circles, there are 3 ways that it can happen. Either the line intersects the circle nowhere, not at all, or the line intersects in one place, namely that it's tangent to the circle, or that the line intersects twice, which is what we saw in 24. When we're talking about lines intersecting planes in 3 dimensions, there's only 2 options. Either your line is parallel with your plane, such that it might not intersect at all, or maybe it pierces through the plane in a single point. Either way, we're going to use the same approach. What does it mean for this line to intersect the plane? It means that the x, y, z coordinate points satisfy both the line and the plane. Now you'll notice that the plane only involves the variables y and z, rendering this x equation useless because the plane doesn't depend on x. So what I'm going to do is I'm going to take my y and z equation, plug it in for y and z in the plane, and solve for t. So I have 2 times 3t plus 3 times negative 1 plus 2t, and that equals 6. This reduces down to a linear equation. So I have 6t minus 3 plus 6t equals 6. 12t equals 9. So t equals 3/4. Now again, they ask for where. We want to come up with an actual point value. So what I'm going to do is I'm going to plug t equals 3/4 into the x, y, and z parametric equations to come up with a point. So x equals 2 minus 3/4. So that's 8/4 minus 3/4 is 5/4. Y equals 3 times 3/4. So that's 9/4. And z equals negative 1 plus 2 times 3/4. So that's negative 1 plus 3/2 would give me 1/2. So the point of intersection here is 5/4, 9/4, and 1/2. All right, so lastly, we would like to analyze 2 separate parametric equations of lines, namely L1 and L2. We want to first show that they intersect, and once we have proven that, we would like to find their point of intersection. Now there's one thing that I really want to stress in this problem. You'll notice that both of these lines are using the same parameter t, but we cannot assume that those parameters are agreeing. So if we think back to our alien example, we can't blindly assume that an alien visiting Earth is going to measure time in the same way that we're going to. So based on that, what I'm going to do is I'm going to rewrite all of these t's as T1s or T2s, depending on whether they correspond to L1 or L2. So for L1, I'm going to express it as x plus 1 equals 4T1, y minus 3 equals T1, and z minus 1 equals 0. And then similarly for L2, so x plus 13 equals 12T1, y minus 1 equals 6, excuse me, I used T1 and I meant to say T2, so let me correct that. This is going to be a 6T2, and z minus 2 equals 3T2. All right, so this is just being extra careful so that we don't mix our t's up, so that we keep in mind that these lines might be parameterized in different ways. Maybe one is traveling quicker along one line than the other. So now I want to show that these intersect. Again, think about what it means to intersect. It means that there is an x, a y, and a z that satisfies both of these equations. So what I'm going to do is first I'm going to equate all of the x's together. Now let's take a look at this equation and let's solve it for x. That would be 4T1 minus 1. And then I want to do the same thing for L2. If I solve for x, that'll give me 12T2 minus 13. So this is one equation. I cannot solve it because it's one equation with two unknowns, but let me set up my other sets of equations. So I'm going to do the same thing for the y's. So I have T1 plus 3 equals 6T2 plus 1. And then for the z equations, I have 1 equals 3T2 plus 2. Now the fact that T1 is missing in the z equation of L1 is going to make things easy for me because I can solve for T2 immediately. So I have 3T2 equals a negative 1, so T2 has to equal negative 1/3. All right, so I have a value for T2. That is to say that if these lines intersect, it must be at the time when the parameter value T2 equals negative 1/3. Otherwise, we have no hope of our z coordinates actually being equal at any point. So now what I'm going to do is I'm going to back substitute. So I'm going to leave the left-hand side in the second equation the same, T1 plus 3. And then I'm going to substitute in negative 1/3 for T2 here. And this is going to allow me to solve for T1. So I get T1 equals 1 minus 3 and then minus 2 for a total of minus 4. So what we're now claiming is that when T1 is negative 4 and when T2 is negative 1/3, that these lines must intersect. But we haven't checked if that satisfies equation 1, because if it doesn't, then it's no good. We need x, y, and z all to be the same within the same point in time at T1 and T2. So let's check equation 1, plugging in T1 and T2. So we have 4 times a negative 4 minus 1, and the question is, does this equal 12 times negative 1/3 minus 13? So on the left-hand side, I have negative 16 minus 1 is negative 17. And again, let's check here. A 12 times a negative 1/3 is negative 4 minus 13. Sure enough, that is negative 17. Yay, happy face. This is checking out. So what this tells me is when T1 is negative 4 and when T2 is negative 3, both L1 and L2 are going to have the same x, y, and z coordinate. This proves intersection. Okay, we just proved that these two lines intersect. Finally, we want to find where they intersect. So you have two choices. You can either plug T1 into L1 or plug T2 into L2. Now, because we showed that they intersect, they're going to give us the same point, so just pick whichever one you prefer. I'll use L1 because I don't want to deal with fractions. So I'm going to have x plus 13 equals 12 times negative 4. So I get x equals negative 13 minus 48, which is a negative 61. Let's see here. Whoops, darn it all. Let's correct that. This 13, geez. Let's just erase all of this. I was looking at L2, but I plugged in for L1. That's all right. We can delete. Let's try this again. So L1, we have x plus 1 equals 4 times negative 4. This is a much more manageable number. So here we get x equals negative 17. I feel good about that. So now we have, let me actually zoom out a bit. Y minus 3 equals negative 4. This gives me y equals a negative 1. And z minus 1 equals 0 gives me z equals 1. So I now have found the point of intersection. It occurs at negative 17, negative 1, and 1. All right, so that's a wrap on 11.5, parametric equations of lines. And in the next section, 11.6, we'll talk about a similar concept, but we're going to expand from lines to planes in 3 space. Until next